Okay, welcome to Objective 9.3. So here we're going to calculate the scale of an aerial photograph. You guys have done some of this already, just in terms of maps rather than photos. So I'm going to probably go through the actual first calculation really quickly, and then I'll start explaining the second part, which is also related. So I'll do a couple examples with those after. So here is an aerial photograph geometry. So I don't have the airplane in here, but this is just the basics of it. So here's the camera, right? So we have the negative plane, which is where the film is. This 0 is the focal point. So the focal point goes from the focal length, or sorry, goes from the negative plane all the way along the focal length, and that is where all of the light rays meet from the lens. So the lens will cause all the light to bend, and then the light will all converge at one point and then pass each other and be like upside down, right? So I'm sure you've heard at some point, maybe your grandparents have talked about it, that a negative plane, everything is upside down. And you do that with your eye too, right? Your eye bends the light, it hits the focal point where the light is all together, and then it goes to the back of your eye and everything's upside down. It's the same thing here. So we have focal length, and then we have something called a positive plane. Now the positive plane does not exist in real life. Like, it's just merely for visualization and so that we can work with math easier. These are exactly the same triangle. Okay, so there's nothing different between them. Just this one's upside down, this one's still right side up. That's all that's there. Then we have the flying height, and the flying height above the ground, so we're just going to say ground for now. The flying height above the ground to here is known as the flying height above the ground. And so that is big H. We use big H to represent that, but usually there's a prime on it. So when we go to do the calculations, you're going to see H prime. So this, like the MGE, just think of that as like a little, there's like a little thing on top instead. And then on the bottom here, we have the principal point that's right down in the center, and then the entire photo along the bottom here. So we can have the ground distance here, and it's related directly to the positive plane, and the positive plane is exactly the same as the negative plane. We use a scale to take from the ground to the positive plane. The other thing that we can think of here is that this triangle, this little one, is a similar triangle to the big one, which means that they're related, and really it's only just a minor scale that we apply. So the math is really easy, but because we already know horizontally how to do that, right? It's 1 over s equals dm over dg. This time around, though, it's distance of the photo over the distance on the ground. So that's all it is. That's the only change that happens. But the other thing is because these are similar triangles, that the vertical also is related in the same way. So I can calculate a scale if I know the vertical information that I'm working with. So, for example, I am given the focal length on an aerial photo. I know what that is. But I also should know the flying height. At least I would hope that the airplane would know that. So if I know the flying height and I know the focal length, I should be able to determine the scale, because I know how much that's being reduced. And that should be the same as what you calculate horizontally. So the idea, if you see a scale on your aerial photo, or if you see it in the metadata, that is just really a prediction, or like I want this as my scale. It is not actually the scale. You actually have to calculate that after, unless it's being processed and that's in the metadata and it says, hey, this is being processed to this particular scale. That's the only time that you can use that. Otherwise, you have to calculate it. And really, this is the exact same process as calculating a map scale. So there are a couple different ways that we can apply looking at these points. So we can either use known points and known coordinates. So we're using known coordinates. We're going to be using we're going to be using 2 points that we like ASCMs perhaps on the ground. They'd be well-defined spots on the ground that we see. So if we can see them on there, now we can use them. So then we just use Pythagorean's theorem because we know the coordinates of it. We use that. And then what we're going to do is measure the same distance on the photo and use the scale equation to calculate the aerial photo. So 1 over s equals distance of the photo over distance on the ground. It's pretty much exactly the same. So this distance is distance on the ground. Because we are dealing with a plane, because we're dealing with a photo, it is like dealing with UTM coordinates because it is flat. So there's distortion already in it. So just take the measurements as they are. Don't try to correct for it, okay? So it's something that's why it's dphoto instead of just dmap. It would be significantly more complicated when you have to actually bring it down to observation. And so just let it be. Okay, so don't complicate this with the rest of like scale factors and everything. This is merely just 1 over s equals dphoto over the distance on the ground. Then we have a map of the area. So if you have a map of the area, you find the area on the map where the aerial photo overlays, and then you measure the distance on the map and calculate the ground distance. So if we know, so we have an old map. This is just like trying to find out the scale of a map that we don't know, right? So you go like, you figure out the distance on the ground. So we have 1 over s equals dm over dg for the map. And we try to calculate dg, which is the ground distance, because we don't know it on the ground. And then we measure the distance on the aerial photo to get the scale. So take that ground measurement. It's going to be the exact same for whether you use the map to calculate it or you use the photo. So this is the same. We can measure this on the photo, and then we can calculate s by you doing that. So you guys have done that before. That should look very familiar. Now we got to be concerned about the vertical values. Because of similar triangles, we can use that vertical information. So as I mentioned, f is the focal length, h prime is the flying height, and we can calculate 1 over s. But what happens if we have terrain that is not even? We have 2 different scales. For example, something that's closer is going to appear larger on the image than something that is further away. It's definitely going to be smaller, which means that now I have 2 different scales on the exact same photograph. So how can we adjust for this? How do we calculate an overall average scale for a map when we're dealing with that? So the most accurate way is to try to find the average elevation of the ground in the photo. So to do that, you find the highest point in the aerial photo, and then you find the lowest point in the aerial photo, and you divide it by 2. So if you need to know the elevation for the highest point, and you need to know the elevation for the lowest point. Don't use any more. So what I mean by that is if I give you 10 different heights and elevations, I don't want you to calculate 10. I want you to find which point is the highest point and which point is the lowest point. If you are having to look this up yourself, Google Earth is actually a really good tool because you can just pull it up. You can try to find the highest point just by like running your mouse over top of it. It gives you a couple like the elevations, and you find, okay, I can write that down, and then you find the lowest one in the aerial photo, and you can write down that one. But only the maximum and minimum. Do not use more, because what that does is it's going to bias it to one side. And so if you have a lot of points, especially these elevation points, and they tend to be clustered over in one particular area, it's going to bias that scale. So we don't want to do that. We want to avoid the bias, and we're just going to use the highest and lowest point, because then it is the overall average of that photo. Those other issues of like having more on one side or whatever, all of that can be corrected with using something called bundle adjustments, and there's other formulas that we can use, and you will learn about that next year in photogrammetry, not in this class. You're only going to find a very simple way to find scale. So we find the average height using maximum and minimum, and then we need to find the flying height above the ground. So the next issue is altimeters read the flying height as above mean sea level. They don't actually read the ground. So to find that, we go back to, remember our formula where we were trying to find out the height of the ground? Thinking way back to that. Um, that's what we're doing here. So we are going to have h, so big H without the prime is my flying height above mean sea level. Okay? Flying height above mean sea level is big H with no apostrophe. Then we can subtract the average height of the ground. So that's what little h averages, is the the average height of the ground between the geoid and the Earth's surface. So that h average, going back to here, is this here, right? So h max plus h min over 2, that gives me the height. Now I'm going to use that value, and I'm going to use my altimeter value to figure out the flying height above the ground. So then for those of you who love pushing them all together into one, this is what our scale calculation becomes. So we have 1 over s equals the focal length divided by my altimeter reading minus the average height of the ground. And then that is really all that you need to do for uneven terrain. So let's just do a quick example of uneven terrain here. And I'm going to pull up my whiteboard. Do this. And it's funny because in the classroom you would see me getting all ready to do this, and I would just be doing it on the whiteboard. But I have like a tablet that I have like a funky little like glove that I get to wear so that I don't cause any like strange things to happen, I guess. So I have to put that on and everything. All right, so using an example, so here's an example. So I find my one height is at 973.41 meters, and I have another height of the ground, which is at 1123.41 meters. Okay? I didn't do that on purpose. I have a tendency to go 341 for like everything at the end. I'm just making up these numbers as I go. So the focal length is 153.346 millimeters. So that's a 6. So we have the focal length, and then my altimeter reading is at 2,627.74 meters. And that's everything that I think I need there. So what is the scale of the photo? So I'm going to break this down into the smaller steps just for those of you who prefer to see it spread out and see the individual steps. So my first step is to figure out what my H average is. And so my H average is 1123.41, right? Because that is my H max. And then I'm going to add H min, which is 973.41. And then I'm going to divide by 2, right? So H average equals H max plus H min over 2. All right, so when we go to calculate that out, we end up with 1048.41 meters. So there's my average. Then I can determine my flying height above the ground. So that is H minus H average. So to do that, I take my altimeter reading, I'm going to say ASL, which is above sea level. So we would say 2627.74 meters minus my 1048.41 meters. And we get a flying height of 1579.33 meters above the ground. Now we can do the full calculation. So 1 over s equals f over h prime, and that equals 153.346 millimeters divided by 1579. I'm going to just do this because I can do that quick math in my head. And then I can calculate so what I'm doing is I'm doing this value multiplied by 1 divided by this value. And I get a scale number. So S is 10299.13. Okay, so if I have a decimal in a scale, I get rid of it and I round up. So my scale value is 10300. And that is my scale for this particular aerial photo. Okay. So I'm going to draw a little quick picture here just so that you can see what's going on with this. So I have my geoid that's below, and then I have my surface like that, and then I'm going to have my flight. So what I'm trying to do is, I guess I could have done that. So I've taken my values for my highest point, which is here. So there's the highest point, and this is the lowest point. So this is H max, and this is H min. Okay. And then what I'm trying to do is find out that center line in between. So I'm trying to find out basically where this is, right? Because that's approximately halfway, so that's like H average. And then on here, I have from here all the way down to here, which is big H. And then I've got the other level, which is from here all the way down to the yellow, which is my H prime. And then if I were to add in my plane for this, I have my next values, which from here to here is F. Okay, so I've got my focal length, which this is thinking that is the positive plane. I have my flying height above the average elevation, and I have my flying height above the ground. I have H max and I have H min. So this is all that's going on in here. So it's quite a bit happening. And but if you can keep this straight, like for example, the H average, what is my average value here? What is, how do I get from the altimeter reading to the flying height above the ground? Well, that makes sense, right? Like I have to go from here to here. And the only way for me to do that is to minus this ground out of here. And I just use an average. So the average is only the top and low and bottom. And then I'm given focal length, I'm given the altimeter reading, and I'm given these ones in this case. If you don't have these ones, you would use Google Earth and you would look it up and determine it that way. So that's an example of how to do this with variable terrain. And so this will be definitely in your assignment at some point for this um, particular module. And we will see you, I guess, in Objective 3 or 9.4. Yeah.